Hey, my name is Stephen Akers, and today I'll be reviewing what I have done for Lab 4 called Macroscopic View of DC and RC Circuits. The whole point of this lab is to basically try to observe how circuits work along with different instruments when they're involved. And we're also going to be seeing how these instruments can change a circuit, like its properties like a current or the potential differences at certain locations within that circuit. The concepts that we're going to be using today will be the node rule and the loop rule, as well as the relationship that we know with current, voltage, and resistance, aka V equals IR. And the only materials that we're going to be using here will be a CKK simulation, and all we need for that is a computer. So for the first part of the experiment, what we're trying to do is basically understand how different instruments work within a circuit. So for example, an ammeter or a voltmeter, what their roles are within the circuit and what they can tell us. And here we also need to find out the potential difference at certain locations on a circuit that we built. So some observations that I made is that the orientation of the emitters did not really affect its readings. So for example, as you can see in the table, for IM1 and I2, both are ammeters. They both read 0.02 amps, whether I oriented them normally or like backwards oriented. Another observation that I made was that the voltmeter actually has infinite resistance. It's basically kind of like a open switch where there's infinite resistance and it's not allowing current to flow through anymore within the circuits. So, so basically, it doesn't act as a wire, but instead as an open switch. Therefore, there's no current that's going to be read within the ammeter. So as you can see in my table for voltmeter, as well as using I1, the ammeter, it does read -3 volts for the potential difference on the voltmeter. However, for the ammeter, it's going to read 0 amps simply because there is no current running through the circuit anymore, simply because of the voltmeter. So continuing this experiment, I had to measure the currents within a circuit that I built, and the current was constant throughout when running it, and that was measured to be around 0.02 amps using the ammeter. Now, throughout the lab, I was also tasked to try to find the potential difference at certain locations. So, for instance, like there's a location called C and there's a location called D, and it had like some separation apart, some length. I don't know how much, but there is some length between C and D, and therefore there can be a potential difference when measuring from C to D location by using the voltmeter. So I did measure those values. So for instance, C to D was -0.959 volts, D to E was 0, E to F was -2.041 volts, F to G was 0, G to H was 0, and H to A was 0 as well. So here we're able to use the loop rule for potential difference. So we know they already give us a graph of the potential difference at certain locations within the circuit. And as we can see, we know that A to C, the potential difference will equal 3 volts. And since we also know the loop rule, which states that if there is a loop occurring, then the potential difference will equal to 0. And so we keep that in mind when trying to see if we're getting the right potential difference values from C to H. And as we see, if we add up all the potential difference values from C to D, D to E, E to F, F to G, and so on and so forth, we should get a value of around -3, and which we do, fortunately. And what this does, it cancels out the potential difference of 3 volts for what they got for A to C, cancels that out, and equaling, making the circuit have a net potential difference equal to 0. And so since it equals to 0, therefore it satisfies the loop rule, which is what we want. So another task that I had to do within the first half of the experiments was I had to find the resistance values at certain locations of the circuit. that I was using. And the way I was able to determine that resistance was by using the rule that resistance equals potential difference divided by current. And I've already measured the potential difference at certain locations. As you can see, C to D will have a potential difference of negative 0.959 volts. And as I stated before, the current throughout the circuit was constant, equaling to 0.02 amps. And so by basically using that rule, potential difference divided by current, I was able to get the values. So for the 47 ohm resistor, I got a resistance of negative 47.95 ohms. At the 100 ohm resistor, I got negative 102.05 ohms. And at any wire on the circuit, there was a resistance of 0 ohms, and also at the ammeter, there was a resistance of 0 ohms, which should be correct because there shouldn't be any resistance within a wire or throughout the ammeter. And now for the capacitor portion of the experiments. Here, what we're trying to do here is that we're going to let a capacitor charge for a certain amount of time, try to let it charge to 9 volts, or to get a reading of 9 volts within the voltmeter. And then once it's charged, we're going to let it discharge for around 20 seconds and try to record the potential difference near the capacitor using our voltmeter. The purpose of that is to try to get an RC value. And we're able to get that RC value by plotting our recorded potential differences and then trying to figure out the slope of that plot, and we can use that to find our RC value. And also, we're supposed to find an RC value by hand and try to compare the two from both the experiment and then what we did by hand. So as you can see, I did manage to get some RC values for the experiments. I got an RC value around 2.83 using the using the slope of the average slope of my recorded values, and it does equal to around 2.83. But the RC value that I did by hand was supposed to be around 6. And of course, 2.83 and 6 are not the same thing. So for me, at least, I did not get RC values that matched. I'm not too sure if this is the way that if I graphed properly or not, but that is what I got. Okay, so to finish things off, I have some post-lab questions to answer. For the first one, what's the difference between a real ammeter and an ideal one, and how would it affect the circuit when we hook it up? And the second question is, again, basically the same thing. What's the difference between a real capacitor and an ideal one? And how quickly do we expect the real capacitor to actually reach full charge? And while comparing that to an ideal capacitor. So for the first question, a real ammeter does have some resistance, while an ideal one, which I use for with the simulation, will not have any resistance, and therefore the ideal ammeter will properly read the current going through the circuits, while an ammeter in real life will not accurately show the current running through the system. Excuse me, the circuits. For the second question, basically the same rule applies here. A real capacitor also does have some resistance, and therefore it's going to take a little bit more time for it to actually reach full charge when we compare that to an ideal capacitor. So we should expect a real capacitor to just have a little bit more time necessary for it to actually get to where it needs to be when we compare that to an ideal one.